Let's look at another example of Hess's law. So in this one, we want to calculate the enthalpy of the reaction for 2 carbon, and this is solid graphite rather than solid that's in the diamond state. And so be careful with these actual um, phases as they're important. So like a solid made out of graphite is different than a solid made out of diamond in the case of carbon, or a solid in a liquid would have a really different enthalpy as well. So this reacts with hydrogen gas to form C2H2 gas. And we have a couple of different reactions that we're going to combine here to build something that is exactly the same. And so looking at this first one, I have the C2H2, sorry, right here, gas, that is my product. It has a bunch of other stuff, and I'm not going to stress out about that too much and hope that most of this cancels away. And if not, I'll come back and make changes. So it might need to be an iterative process. So I'm going to focus on that. I'm also going to then focus on the carbon right here. I've got 2 carbon with graphene, and I have that in my second equation. So that's good. And then the last one I'm going to focus on is this hydrogen gas, and I can find that in my third one. And it's not anywhere else. So I need all 3 of these reactions to solve that problem. So once I identify where I can get these reactants and products from for the reaction I'm interested in, now I can go about manipulating the chemical equations of the steps to get to that reaction or the stepwise reactions. So that way I can manipulate this into being the equation I want. So for the first one, my C2H2 is listed as a reactant instead of the product that I need. And so I really need to flip this reaction. And so to do that, to make my reactant a product, I multiply it by -1, which means I multiply my enthalpy of the reaction by -1 as well. And that means the enthalpy of the reaction becomes this positive value right here, this positive 1299.6 kilojoules. And when I flip it, that takes that C2H2 and it makes it a product, along with that 5/2 oxygen. And then my products become my reactants on that one. All right, looking at the next one for my carbon. So I have a coefficient of 2 in my reaction that I'm interested in, and this reaction doesn't have a coefficient. So I need to multiply everything, every coefficient by 2 in this chemical reaction. That means I have to also multiply my enthalpy of the reaction by 2. So that's going to give me an enthalpy of reaction that's negative 787.0, and it's going to increase the coefficients of all of the reactants and products of this reaction by 2. Now, the carbon is a reactant in this reaction, just like in the one I'm interested in, so I don't need to multiply it by -1. All right, looking at our last one, the hydrogen. It's a reactant just like in the reaction that I'm interested in, so I don't need to multiply it by -1. It has a coefficient of 1 and a coefficient of 1, so it has the right coefficient. So this doesn't need to be manipulated at all, and the enthalpy stays the same. Now I'm going to add all 3 of these reactions up together by taking everything on the reactant side and putting it on the same reactant side of an equation. And take everything on a product side and putting it on the other side of the arrow for the product side. And I get this really long thing down here at the bottom. And I'm going to highlight the things that I'm most interested in, right? So I have my C2H2, and I have my hydrogen gas, and I have my 2 carbon. So I have all the components of this reaction. Now the question is, does everything else cancel out, or am I left with other things? Because if everything else doesn't cancel out, then I'm not going to be able to calculate the enthalpy of the reaction I'm interested in. I'm going to have to go back to the drawing board. So looking at this, I can see, all right, I've got 2 carbon dioxide on my reactant side and my product side. So I can get rid of those. Great. I have a water on my reactant side and a water on my product side. I can get rid of those too. I have 2 oxygen and a half of an oxygen. So that's going to be 2.5 oxygen or 5/2. And I have a 5/2 oxygen on my product side. So I can get rid of all of those oxygens, and everything cancels out except the carbon, hydrogen, and C2H2. So this reduces down to exactly the reaction that I want, which means for my enthalpy of the reaction, I'm taking the sum of that positive 1299.6, negative 787, and negative 285.8 kilojoules. And those are the manipulated enthalpies for each of the three reactions added up together, and it gets me an enthalpy of 226.8 kilojoules.